Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to my beloved lecturer Puan Nurul Shazni binti Mat Saleh and to my fellow friends. Today we will be presenting about our task 2, which is a video presentation of the course appreciation of mathematics. Today, we are presenting a topic that sits at the very heart of how we understand natural world. Our presentation is titled Application of Natural Science: The Beauty of Logistic Model in Nature. My name is Amria Shika binti Marzairi and my partner is Nur Shazwani binti Zainan, and we are from Mathematics 3. Throughout this 30-minute session, my partner and I will guide you through a journey of mathematical appreciation. We often think of math as just a number on a page, but in the context of natural science, math is a language. It is the language of survival, of limits, and of balance. As you can see on these opening slides, our focus is the logistic model, a mathematical framework that serves as the bridge between the raw, often scary, unpredictable of nature and the structured progress of human knowledge. We will show you how this model is the foundation of modern civilization and why it is essential for every digital citizen to understand.
Thank you, Amber. Let's look at the first concept on our slide. Moving beyond linear growth. Why it is important. In our daily education, we are often taught linear logic. If one tree produces 10 apples, then 100 trees must produce 1,000. However, as we argue in our report, nature does not follow a straight line. If a population grew without any restriction, it would follow what we call a J-curve, an exponential explosion that eventually leads to a catastrophic crash. The introduction of the logistic model is our reality check. It introduced the concept of environmental resistance. This is the friction of the real world: limited nutrients, lack of space, and competition between species. This is the friction of the real world: limited nutrients, lack of space, and competition between species. By the end of this slide, we want you to understand that the S-curve you see in our material isn't just a shape. It is a representation of nature's self-governance. It is the point where the biological urge to expand meets the physical reality of a finite planet.
Now, let's direct our attentions to the mathematical engineering behind this model. This equation on the slides, dp per dt is equal to rp brackets 1 minus p per k close of brackets, is perhaps one of the most important formula in biology. Let's break down these variables. P is represented by our populations. R is the intrinsic rate of increase or the biological potentials. But look at K, the carrying capacity. This is the golden number. It represents a maximum population in an environment that can sustain indefinitely. The true beauty lies in the bracket terms, brackets 1 minus p per k, close of brackets. Think of it as a dimmer switch. When the population P is very small, this switch is wide open and growth is fast. But as P starts to equal K, the fraction becomes 1. And 1 minus 1 is 0. The growth stops. This creates a sigmoid curve. It is a perfect self-correcting feedback loop that ensures a specific and that ensures a specific species does not destroy its own environment. It is the mathematical definition of sustainability. Okay.
So, how does a scientist take the formula and turn it into a conservation plan? We follow the operational flow shown on our slide. It begins with the input phase. This is the de- this is the detective work. We collect data on birth rate, mortality, and resource availability. We don't just look at the animals, we look at the soil, the water, and the climate. Next is the processing phase. This is where we apply the appreciation of mathematics. We use the logistic equation to find the inflection point. This is the specific moment in a population growth where it is moving at its absolute maximum speed. Finally, we reach the output phase. This gives us a predicting trajectory, a map of the future. This allows for preemptive management instead of reacting to a crisis after it happened. The logistic model allows us to see the crisis coming years in advance, giving us the power to change the outcome.
This brings us to the core of the section of our report, which is the computational thinking. This is not just using a computer. It is a method of problem solving that we have integrated in our studies of natural science. We often use four distinct pillars. The first pillar is decomposition. We don't look at forests as one giant mystery. We break it down into sub-problems. What is food supply? What is the predator count? What is the square footage of the habitats? By solving these smaller parts, the big problem becomes more clearer. Secondly, pattern pattern recognition. We notice a recurring truth, whether it is bacteria in a petri dish, wolves in the forest, or even the spread of a new technology in a market. They all follow the same S curve. This pattern is likely universal. The third pillar is abstraction. This is the art of filtering the noises, the individual personality of an animal or one day rainstorm, and focus only on the core variables that affects the carrying capacity. And the fourth pillar, which is the last pillar, is the algorithm designs. We have turned the logistic equation into a step-by-step logical rule. If P is less than 50% of K, then do X. If P is 90% of K, then do Y. This algorithmic approach allows us to create standardized softwares that can protect any ecosystem of Earth. It turns messy biology into clean but logical and actionable parts. It turns messy biology into clean, logical, and actionable stats.
Now, let's apply that computational thinking to a real-world scenario. This reintroduce of work. This is a classic case study in our report. Imagine we have a park where the deer population is out of control. We decide to bring the wolf to restore balance. We set our initial carrying capacity K at 100 wolves based on the deer population. But as we know, Nature is dynamic. If a severe winter or a drought kills off 40% of the deer, the food source for our world has the food source for our world has vanished. Using the logistic model, we can immediately recalculate. Our abstraction tells us that the deer count has dropped. Our algorithm then tells us that the new K is now 60 worth, not 100. Because we have this model, we can proactively manage the wolf population. We can avoid a boom and burst cycle where the wolf overhunt and then starve to death. This is the difference between an accidental This is the difference between an accidental extinction and a successful conservation effort. If it shows that math isn't just for the classroom, but it is for survival. It is for the but it is for the survival of the wilderness.
As we move towards the conclusion, we must recognize that the logistic model is an industry standard. It is used daily by World Health Organization to track pandemics. When global leaders talk about flattering the curves, these are literally referencing to the transitions of the exponential phase to our S-curve of the stable plateau of the logistic model. In the corporate world, this model is used for market saturation studies. In the fishing industry, it is used to calculate the maximum sustainable yield. It ensures that we don't have it ensures that we don't harvest so much today that there will be nothing left in the tomorrow and in the future. As we note in our final verdict, being a digital citizen in the 21st century means having the data literacy to understand these limits. It allows the public to see through sensational claims of infinite growth and understand the mathematical reality of our planet constraints. This model is not merely an academic concept, but a real-world industry standard used by major global organizations. A clear example can be seen during COVID-19 pandemics, where institutions like World Health Organization and and national health ministries applied this model in decision making. The phrase "flatten the curve", which became widely known during the pandemic, is directly related to the logistic growth model in the early stages. The number of infected individuals increased rapidly, representing the exponential or log phase. However, if this growth continued unchecked, the total number of cases represented as P would exceed the carrying capacity K of healthcare systems. Carrying capacity refers to the maximum number of patients that hospital can handle, including available beds, medical staff, oxygen supply, and equipment. When this limit is exceeded, the system becomes overwhelmed and may collapse. To prevent this, government introduced interventions such as social distancing, lockdowns, and vaccine programs. These measures were designed to reduce growth rate R in the model. As a result, the curve becomes less steep, ensure that the number of cases remain below the carrying capacity. This will allow the healthcare system to continue functionally, efficiently, and ultimately help saving lives. Beyond healthcare, the same model is applied in industries such as fisheries and forestry. In fisheries, the concept of maximum sustainable yield is used to determine the optimal level of harvesting. This occurs at the point where the population grows at its fastest rate, which is the midpoint of the logistic curve. By harvesting at this level, the population remains stable and continues to reproduce efficiently. Overharvesting can cause the population to decline beyond recovery, while controlled harvesting ensures long-term sustainability. Therefore, the logistic models plays a crucial role in balancing resources use and preservation, demonstrating how mathematics can guide practical and responsible decision making.
An understanding of this model is also essential in shaping us into responsible digital citizens. In today's world, we are constantly exposed to large amounts of data, information, and prediction through social media, new platforms, and digital technologies. Many of these messages promote the idea of continuous or infinite growth, whether in business, technology, or economic development. However, by applying the logic of the logistic model, we can recognize that such claims are often unrealistic. The idea of unlimited growth, sometimes referred to as a J-curve fantasy, ignores the existence of natural limits. In reality, every system every system has a carrying capacity, represented by K, whether it involves whether it involves physical resources, technological infrastructure, or human capability. With this understanding, we become more critical and analytic when evaluating information. Instead of accepting claims at face value, we begin to question their feasibility by considering factors such as limits, sustainability, and long-term impact. This is a key aspect of digital citizenship, which involves responsible and informed participation in the digital world. Being data literate allows us to distinguish between realistic projection and exaggerated claim, reducing the influence of misinformation. It also encourages a shift towards sustainable thinking, where the focus is placed not only on rapid growth, but also on maintaining balance and stability over time. In this way, the logistic model provides a framework for making logical and responsible decisions. By applying this knowledge, we ensure that progress in society remains structured, realistic, and sustainable within the limits of available resources. In conclusion, the logistic model is far more than just a mathematical formula or an abstract concept that exists only on paper. As our report has highlighted, it represents a fundamental truth of the natural science and serves as a powerful tool to understand the world around us. At the first glance, many biological and environmental systems may appear chaotic, random, and unpredictable. However, through the lens of mathematics, particularly the logistic model, we begin to see that there is actually an underlying structure covering this system. This model demonstrates that even the most complex population, whether they are animal, bacteria, or even human scientists, tend to follow a logical and predictable pattern of growth. where certain conditions are met. But beyond theory, what makes the logistic model truly powerful is its application in real life. For example, in ecology, scientists use to predict animal population growth and prevent extinctions. In medicine, it helps researchers understand how bacteria or virus spread in a limited environment. Even in business, companies use similar models to predict market growth and customer behavior. This shows that the logistic model is not just this show that the logistic model is not just limited to one field. It is universal. It connects different disciplines and allows us to see patterns across various aspects of life.
One of the most important elements of the logistic model is the concept of carrying capacity, represented by the constant K. This value reminds us that resources in real life world are always limited. No matter how fast population grows initially, it cannot continue indefinitely. Eventually, factors such as food availability, space, competitions, and environmental resistance will slow down that growth. This idea teaches us that important life lesson as well. In a world that constantly pushes for growth, successes, and expansions, these logistic models reminds us that limits are natural limits are natural and necessary. Growth model without control can lead to imbalance and sometimes even collapse. This concept This concept is especially relevant in today's modern world as we face global challenges such as overpopulation, climate change, and resource depletion. The logistic model serves as a reminder that sustainable thinking is not just important, it is essential. We must learn to we must learn to balance development with preservation and ambition with responsibility. In addition, the integration of mathematics and computational thinking plays a crucial role in helping us navigate these modern complexities. Mathematics allows us to build models, make predictions, and analyze patterns with precision. Meanwhile, the computational thinking skills helps us to approach problems in a structured and logical way by breaking them down, recognizing patterns, and designing step-by-step solutions. These skills are not only useful in academics, but also in real-life decision making. They help us they help us to become more analytical, more organized, and more capable of solving complex problems efficiently. More, Moreover, mathematics remains an essential foundation of modern civilization. It is present in almost everything we do, from technology we use to the if from the technology we use daily to the infrastructures we depend on, and even in the system that runs on economy. Mathematics act as a bridge between unpredictability of nature and the structured progress of human knowledge. Without mathematics, we would not be able to understand patterns, make accurate predictions, or develop innovations that improve our quality of life. It transforms uncertainty into clarity and complexity to understanding. As we reflect on discussion today, we hope that you now see the logistic model in a new light. What may have happened initially seems like just a simple S-shaped curve could actually represent a deeper principle about balance, limitations, and sustainability in the real world.
It reminds us that everything in life has a pattern, and more importantly, a limit. And by understanding this limit, we can make a better decisions, not only as a student, but also as a future leaders and contribute to society. Before we end, we would also like to emphasize that learning mathematical oh, sorry. But before we end, we would also like to emphasize that learning mathematics is not just about memorizing formulas. It is about developing a way of thinking, a mindset that allows us to question, analyze, and understand the world more deeply. With that, we truly hope that this presentation has given you a new appreciation for the beauty and importance of mathematics, especially in explaining real-world phenomena through models like the logistic model. Thank you very much for your time, your attention, and your patience throughout this presentation. Bye bye.